Welcome to our Bioprocess Engineering online tutorial on continuous microbial fermentations. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. Industrial microbial fermenters operate in three distinct modes. Batch mode: the entire fermentation medium is introduced at the start, with no further additions or removals during the process. Continuous mode: fresh medium is continuously fed into the fermenter, while an equal amount of culture is simultaneously withdrawn. Fed batch or semi-continuous mode: a portion of the medium is added initially, and the remaining part is gradually fed over time without removing culture. The choice of the optimal fermentation mode depends on the specific microbial transformation being performed, as each approach offers advantages for different processes. In this tutorial, you will explore continuous microbial fermentation. The following topics will be covered: principles of continuous fermentation, main challenges in industrial applications, fermentation dynamics in steady state, optimal operation and oxygen transfer limitations. To illustrate these principles and concepts, we will use a continuous bacterial fermentation process as a working example. When operated in continuous mode, the fermenter is first filled with fresh medium and then inoculated with microbial cells. The process initially proceeds as a batch phase, during which the cells adapt to their new environment and begin to grow. After this adaptation period, a continuous flow of fresh feed medium is gradually introduced into the fermenter. At the same time, an equal flow of culture broth is withdrawn in order to maintain a constant working volume. At a fixed medium flow rate, the system enters a dynamic phase in which substrate and biomass concentrations vary over time. Eventually, the process may reach a steady state, characterized by constant substrate and biomass concentrations within the fermenter. One of the main advantages of continuous fermentation is the ability to operate microbial processes under prolonged nutrient-limiting conditions. Most commonly, the carbon source is limiting. However, other essential nutrients, such as nitrogen or phosphorus, can also be restricted to optimize microbial metabolism. Operating under substrate limitation or at reduced growth rates offers several important benefits. Minimized metabolic overflow. Limiting nutrients reduces the formation of unwanted byproducts typically associated with rapid growth. Enhanced production of non-growth associated metabolites. Many industrially valuable compounds, including secondary metabolites, are produced more efficiently under nutrient-limited conditions. Lower oxygen demand. Reduced growth rates decrease oxygen consumption and help prevent oxygen limitation at high biomass concentrations. By carefully controlling nutrient supply, continuous fermentation can therefore maximize both productivity and overall process efficiency. A second key advantage of continuous fermentation is its ability to sustain steady-state production over extended periods of time, ranging from days to weeks or even months. In contrast to batch processes, which are operated in discrete cycles and require downtime between runs for emptying, cleaning, sterilization, and refilling. Continuous fermentation operates without interruption. As a result, downtime is greatly reduced, leading to higher overall productivity on an hourly basis. A major practical challenge and limitation of continuous fermentation is the maintenance of sterility over prolonged operation. Under laboratory conditions, continuous fermentations can be maintained safely for several weeks. In industrial environments, however, the risk of contamination is significantly higher, particularly for processes operated at near neutral pH and at temperatures in the 30 to 35 degrees Celsius range. Consequently, continuous fermentation is more readily suited to non-sterile processes or to fermentations operated under more acidic conditions, where the risk of contamination is reduced. A second operational challenge in continuous fermentation is achieving and maintaining a steady-state biomass concentration. In continuous operation, cellular biomass is continuously produced through growth and simultaneously removed with the outflow. A steady state is reached when the biomass production rate equals the biomass removal rate. The biomass removal rate from the fermenter is not inherently limited, as it increases directly with the medium flow rate. In contrast, the biomass production rate is constrained by the cell's specific growth rate. Consequently, operating at excessively high medium flow rates may lead to cellular washout, where biomass is removed faster than it can be produced. This challenge of maintaining a steady state is even more pronounced in fermentations aimed at metabolite or protein production, as continuous operation requires the simultaneous and prolonged maintenance of both biomass and product formation within the fermenter. This is readily achievable for growth-associated metabolites, whose production is directly linked to cell growth. In contrast, it is more challenging for non-growth-associated metabolites, particularly when high product formation is favored at reduced growth rates or under conditions of growth arrest. Once steady-state operation has been established, the next challenge is the optimization of the continuous fermentation process. The two main operational variables are the composition of the feed medium, particularly the carbon source concentration, and the continuous feed flow rate. These parameters are typically adjusted to achieve the highest possible fermenter productivity. In aerobic fermentations, an additional challenge is the prevention of oxygen limitation. Excessively low dissolved oxygen concentrations may induce undesirable metabolic shifts, ultimately reducing process performance. Continuous fermentations are commonly used at the laboratory scale for kinetic analysis. They represent a powerful tool for the precise study of microbial kinetics under controlled substrate-limiting conditions. At steady state, under chemostat operation, it is possible to investigate how cells adapt their growth and metabolism to prolonged nutrient limitation, and to accurately determine their specific rates of growth, substrate consumption, and metabolite production. At large scale, continuous fermentation processes are widely applied in water and waste treatments. Continuous aerobic processes are commonly used for water treatment, such as activated sludge systems in biological denitrification. In addition, continuous anaerobic digestion is extensively employed for the treatment of organic wastes and for the production of methane-rich biogas. Major industrial applications of continuous fermentation include the production of cellular biomass, particularly yeast cells, as well as the production of growth-associated metabolites such as ethanol and organic acids, for example, lactic and acetic acids. These processes are particularly well suited to continuous operation because they do not require stringent sterility conditions, allowing long-term and stable operation at industrial scale. In this tutorial, the continuous operation and optimization strategy are demonstrated using a fermentation process that involves the growth of bacteria on a sugar substrate. The fermentation takes place in a 1,000-liter stirred and aerated industrial fermenter. The optimal continuous operation strategy is investigated using a simulation model of the fermentation process. This knowledge model incorporates the rate-limiting factors of bacterial growth and metabolism, as well as oxygen transfer. The simulation model, acting as a digital twin of the fermentation, enables the operation of continuous fermentations under various conditions. This approach helps to better understand and assess the impact of different operational variables, and provides valuable insights for optimizing these variables to maximize fermenter productivity. The methodology used for fermentation modeling is introduced in a previous tutorial on microbial fermentation simulation models. Constructing a fermentation simulation model involves deriving the mathematical relationships that describe the time-dependent variations in the concentrations of the different components in the medium. This modeling methodology follows the concept of the modeling triangle, which integrates material balance equations, expressing the principle of mass conservation, with thermodynamic and kinetic laws, describing the underlying physical and biochemical phenomena. In the example of bacterial biomass production, the kinetic laws predict the rates of cell growth, metabolism, and oxygen transfer, while the thermodynamic law is used to calculate oxygen solubility in the liquid phase. At the core of the fermentation simulation model is a set of laws that relate the specific rates of cell growth, sugar consumption, and oxygen consumption to the composition of the culture medium. The most commonly used model for bacterial growth kinetics suggests that the growth rate reaches a maximum at high sugar concentrations and decreases when sugar becomes limited. According to the Monod rate law, the specific growth rate mu is given by mu equals mu max S over Ks plus S, where mu max is the maximum specific growth rate, S is the sugar concentration, Ks is the half-saturation constant. The specific sugar consumption rate, Qs, in gram sugar per gram of biomass per hour, is typically proportional to the cell-specific growth rate. Qs equals 1 over Yx over S mu, with a stoichiometric yield coefficient Yx over S in gram biomass produced per gram sugar consumed. Similarly, the specific oxygen consumption rate QO2 in gram oxygen per gram of biomass per hour is also proportional to the cell-specific growth rate. QO2 equals YO2 over X mu with a stoichiometric coefficient YO2 over X in gram oxygen consumed per gram biomass produced. For the bacterial strain used in the fermentation simulation, the kinetic laws parameters are as follows. Mu max equals 0.4 hour minus 1, Ks equals 0.5 gram per liter, Yx over S equals 0.5 gram biomass per gram sugar, and YO2 over X equals 0.7 gram oxygen per gram biomass. The time variation of the cellular biomass concentration X in gram per liter is described by the instantaneous mass balance for the cells in the fermenter. Under continuous operating conditions, the fermenter is fed with sterile medium at a constant volumetric flow rate Q liters per hour, while an equal flow rate is withdrawn from the reactor. As a result, the working medium volume V of the fermenter remains constant. Cellular biomass is produced inside the fermenter through microbial growth and is simultaneously removed with the outlet stream. Since the fermenter is assumed to be perfectly mixed, the biomass concentration in the outlet stream is equal to the biomass concentration inside the reactor. The instantaneous biomass balance, expressed in gram of biomass per hour, on the whole fermenter can therefore be written as cellular production rate Rx equals outlet rate Qx plus internal mass variation rate d mx over dt. The biomass mass mx is the product of the volume V by the biomass concentration x. The biomass production rate Rx is given by the product of the specific growth rate mu, the biomass concentration x, and the medium volume V. The resulting biomass balance is mu xv equals Qx plus V dx over dt. Dividing by the medium volume V yields the governing differential equation for the temporal evolution of the biomass concentration. Dx over dt equals mu x plus Q over Vx. The time variation of the sugar concentration S in grams per liter is described by the instantaneous sugar mass balance in the fermenter. Sugar is continuously supplied to the fermenter with the inlet medium at a concentration S feed, while the residual sugar at concentration S is continuously removed with the outlet stream at the same volumetric flow rate Q. The instantaneous sugar mass balance, expressed in grams of sugar per hour, can therefore be written as sugar inlet rate QS feed minus sugar consumption rate RS in the fermenter equals sugar outlet rate QS plus variation rate of the internal sugar mass dMs over dt. The sugar mass Ms is the product of the volume V by the sugar concentration S. The sugar consumption rate Rs is given by the product of the specific sugar consumption rate Qs, the biomass concentration X, and the medium volume V. The resulting sugar balance is Qs feed minus QSXV equals Qs plus VDS over dt. Dividing by the medium volume V yields the governing differential equation for the temporal evolution of the sugar concentration, ds over dt equals minus QSX plus Q over V S feed minus S. According to the instantaneous biomass and substrate mass balances, the temporal variations of biomass and substrate concentrations during continuous fermentation depend on the ratio between the volumetric flow rate Q and the medium volume V in the fermenter. This ratio is known as the dilution rate, D. It represents the volume of fresh medium in liters, fed per liter of reactor volume per hour. The dynamics of continuous fermentation can also be analyzed in terms of the residence time, or mean transit time, of the culture medium within the fermenter. The residence time tau, which is the inverse of the dilution rate, is defined as the ratio between the reactor volume and the volumetric flow rate. The two differential equations describing the temporal variations of biomass and sugar concentrations are solved by numerical integration. Numerical integration can be conveniently performed using spreadsheets. In numerical integration, the exact solution curve is approximated by a polygonal curve composed of successive points connected by straight-line segments. These points are separated by a fixed time increment, delta t. For the biomass concentration X, the integration starts from the initial concentration x0. A straight-line segment is drawn from x0 with a slope equal to the time derivative dx over dt, evaluated at time t equals 0. This yields the biomass concentration x1 at time t1 equals delta t. At time t1, the derivative dx over dt is recalculated using the updated values of the state variables, and a new straight-line segment is drawn up to time t2, giving the concentration x2. This procedure is repeated to compute x3 and the subsequent biomass concentrations over the entire time interval of interest. When applied to the two differential equations, numerical integration provides the temporal evolution of sugar and biomass concentrations during the initial batch phase and the subsequent continuous operation until steady-state concentrations are ultimately reached. Following the initial batch phase, the dynamics of continuous fermentation is mainly governed by the dilution rate D. In the bacterial growth example considered here, the process starts with an initial batch phase lasting 5 hours at an initial sugar concentration of 10 grams per liter. The feed sugar concentration during continuous operation is also 10 grams per liter. After a transient continuous operation phase, steady-state sugar and biomass concentrations are reached after approximately 5 residence times. The temporal variations of sugar and biomass concentrations are analyzed below. At a low dilution rate of D equals 0.2 hour minus 1, corresponding to a long residence time of 5 hours, the system reaches a steady state, characterized by a low residual substrate concentration and a high biomass concentration. At an intermediate dilution rate of D equals 0.4 hour minus 1, the fermentation dynamics lead to intermediate steady-state concentrations of both substrate and biomass. At a high dilution rate of D equals 0.6 hour minus 1, Complete washout of the cells from the fermenter is observed at steady state. At such high feed rates, the rate at which cells are removed from the reactor exceeds their growth rate, leading to cell loss by dilution. In this case, the steady-state sugar concentration equals the feed sugar concentration. It should be noted that the initial batch phase influences the transient evolution of substrate in biomass concentrations, but does not affect their final steady-state values, which are determined solely by the operating conditions of the continuous process. The steady-state substrate and biomass concentrations can be predicted from the instantaneous mass balances by setting the variation rate terms equal to zero. The steady-state biomass concentration XSS is obtained from the stationary biomass balance. 0 equals mu XSS minus dXSS. This implies that, at steady state, the rate of cell production equals the rate of cell removal from the fermenter. Mu XSS equals dXSS. Dividing by XSS yields the fundamental steady-state relation, mu equals d. This key result of continuous fermentation indicates that steady state is reached when the microorganisms adjust their specific growth rate to match the dilution rate imposed by the operation of the fermenter. The steady-state substrate concentration SSS is determined from the stationary substrate balance. 0 equals minus QSXSS plus D S feed minus SSS, or equivalently, QSXSS equals D S feed minus SSS. This relation shows that, at steady state, the volumetric substrate consumption rate is equal to the dilution rate, multiplied by the difference between the feed substrate concentration and the residual substrate concentration in the fermenter. The steady-state substrate concentration SSS is obtained from the steady-state biomass balance. By expressing the specific growth rate using Monod's law, the steady-state biomass balance becomes mu max SSS over Ks plus SSS equals D. Rearranging this expression gives mu max SSS equals DKS plus DSSS, which leads to the steady-state substrate concentration SSS equals DKS divided by mu max minus D. The steady-state biomass concentration XSS is then determined from the steady-state substrate balance. By expressing the specific substrate consumption rate in terms of the biomass growth rate and the yield coefficient Yx over S, the substrate balance becomes 1 over Yx over S, mu XSS equals D S feed minus SSS. Using the steady-state condition mu equals D, this expression simplifies to XS equals Yx over S, S feed minus SSS. This result shows that the steady-state biomass concentration is directly proportional to the amount of substrate consumed between the feed and the fermenter outlet. What are the influences of dilution rate and feed sugar concentration on the steady-state sugar and biomass concentrations? The steady-state substrate concentration SSS depends solely on the dilution rate D. It is independent of the substrate concentration in the feed. During continuous fermentation, the substrate concentration in the reactor automatically adjusts through microbial activity until the specific growth rate of the cells equals the dilution rate. At very low dilution rates, corresponding to long residence times of the medium in the fermenter, the substrate is almost completely consumed before leaving the reactor, resulting in very low steady-state substrate concentrations. As the dilution rate increases, corresponding to shorter residence times, the steady-state substrate concentration increases. At sufficiently high dilution rates, cell washout occurs, and the steady-state substrate concentration approaches the feed substrate concentration. In contrast, the steady-state biomass concentration, XSS, depends on both the dilution rate and the substrate concentration in the feed. Increasing the feed substrate concentration leads to higher steady-state biomass levels. The biomass concentration is maximal at low dilution rates, when the substrate is fully consumed. As the dilution rate increases and the residence time decreases, the steady-state biomass concentration decreases. At excessively high dilution rates, the biomass concentration falls to zero, indicating that the rate at which cells are removed from the fermenter exceeds their rate of growth within the reactor. What is the critical dilution rate at which cellular washout occurs at steady state? Cellular washout at steady state occurs when the biomass concentration in the fermenter becomes zero. Under these conditions, no substrate is consumed, and the substrate concentration inside the fermenter is equal to the feed substrate concentration S feed. The critical dilution rate at which washout occurs, denoted D washout, is equal to the specific growth rate of the cells, evaluated at the feed substrate concentration. Using Monod's kinetics, this condition can be written as D washout equals mu max S feed divided by Ks plus S feed. In most practical situations, the feed substrate concentration is much larger than the monody constant Ks. As a result, the washout dilution rate approaches the maximum specific growth rate. This result implies that continuous cell production cannot be sustained at dilution rates higher than the maximum specific growth rate of the microorganism, since cells are then removed from the fermenter faster than they can reproduce. The following section of the tutorial presents the optimization strategy for continuous fermentation. The initial batch phase is kept relatively short, typically a few hours, its purpose being to adapt the inoculated cells to the culture medium and to initiate cell growth. The initial sugar concentration S0 is fixed at a value slightly higher than the expected steady-state substrate concentration SSS. This strategy helps shorten the transient period following the start of continuous operation. During continuous operation, the dilution rate D is the primary operational variable to be optimized. It directly determines both the steady-state specific growth rate of the cells and the steady-state substrate concentration SSS. The second key operational variable is the feed substrate concentration S feed. For a given stoichiometric yield coefficient Yx over S, it determines the steady-state biomass concentration XSS that can be achieved. The most commonly used optimization criterion in fermentation processes is the production cost per kilogram of product. This cost is strongly influenced by the productivity of the fermenter. In the case of cellular biomass production, the volumetric productivity (prod(x), expressed in grams of biomass per liter per hour, is defined as the mass of biomass produced per unit fermenter volume and per unit time. Productivity therefore represents the hourly efficiency of fermenter utilization and is a key parameter for the economic optimization of continuous fermentation processes. How to calculate the fermenter productivity for the continuous fermentation operated at steady state? During a continuous steady-state operation time Tc, the mass of produced cells Mx is equal to the product of the outlet flow rate Q, the operation time Tc, and the steady-state biomass concentration XSS. The steady-state biomass productivity is thus calculated as prod x equals Q Tc XSS divided by VTC, which simplifies to prod x equals dxss. Substituting the steady-state expression of the biomass concentration yields, prod x equals dyx over s, s feed minus SSS. By expressing the steady-state substrate concentration as a function of the dilution rate using Monod kinetics, the biomass productivity can be written explicitly as a function of the dilution rate, prod x equals dyx over s, s feed minus dks over mu max minus d. This expression forms the basis for determining the optimal dilution rate that maximizes biomass productivity in continuous fermentation. The productivity of a continuous fermenter depends on both the dilution rate and the substrate concentration in the feed. For a given feed substrate concentration, productivity increases with the dilution rate. That is, with the specific growth rate of the cells, until a maximum value is reached. The dilution rate corresponding to maximum productivity is generally close to the critical dilution rate for cellular washout. Beyond the dilution rate yielding maximum productivity, fermenter productivity decreases sharply as washout conditions are approached. It is important to note that the highest productivity is not achieved at the maximum biomass concentration, which occurs at low dilution rates, but rather at intermediate dilution rates, where an optimal balance is established between biomass concentration and cell growth rate. In addition, fermenter productivity increases with increasing substrate concentration in the feed, reflecting the associated increase in steady-state biomass concentration, provided that oxygen transfer does not become limiting. For aerobic fermentations in all operational modes, batch, continuous, fed batch, the maximum achievable fermenter productivity and biomass concentration are limited by the supply of oxygen and its transfer from the gas phase to the fermentation medium. The evaluation of oxygen transfer limitations as fermenter scale increases is discussed in detail in the tutorial Scale-up of microbial fermentation aeration. Oxygen limitations arise when the dissolved oxygen concentration in the liquid phase falls to critically low levels. The dissolved oxygen concentration in the fermentation medium results from the instantaneous oxygen balance in the liquid phase of the fermenter. At any given time, this balance expresses the equality between the rate of oxygen transfer from the gas phase to the liquid and the rate of oxygen consumption by the microbial cells. When expressed per unit volume of liquid, this balance can be written as JO 2/3 equals RO 2/3. This relationship is commonly expressed using the terminology oxygen transfer rate, OTR, equals oxygen uptake rate, OUR. The volumetric oxygen consumption rate, RO 2/3 gram oxygen per liter hour, is equal to the product of the specific oxygen consumption rate, QO2, and the biomass concentration X. The specific oxygen consumption rate, QO2, is proportional to the specific growth rate mu and can be expressed as QO2 equals YO2 over X mu. Under steady-state continuous operation, the specific growth rate is equal to the dilution rate, mu equals D. The volumetric oxygen consumption rate therefore becomes RO 2/3 equals YO2 over X dXSS. Since at steady state, the biomass productivity is given by prod X equals dXSS, the volumetric oxygen consumption rate can be written as RO 2/3 equals YO2 over X prod X. As a consequence, the volumetric oxygen consumption rate exhibits trends similar to those of biomass productivity with respect to variations in dilution rate and feed substrate concentration. To assess whether the oxygen consumption rate of the culture can be matched by oxygen transfer within the fermenter, the maximum usable volumetric oxygen transfer rate, JO 2/3 max, must be evaluated. The volumetric oxygen transfer rate in gram oxygen per liter hour is given by JO 2/3 equals KLA O2 star mean minus O2L, where KLA is the volumetric oxygen transfer coefficient. O2 star mean is the mean oxygen solubility in the fermenter medium. O2L is the dissolved oxygen concentration in the medium. The oxygen transfer rate increases with the driving force, O2 star mean minus O2L, and would theoretically be maximal if the dissolved oxygen concentration were allowed to approach zero. In practice, however, the dissolved oxygen concentration cannot be reduced arbitrarily. Below a critical minimum value, O2L mini, cells experience oxygen limitation, leading to reduced growth rates and potentially to the formation of undesired byproducts. Consequently, the maximum oxygen transfer rate that can be utilized without inducing oxygen limitation is given by JO 2/3 max equals KLA O2 star mean minus O2L mini. This parameter defines the upper bound for oxygen supply in aerobic fermentations and is a key constraint in process optimization. To avoid oxygen limitation, the volumetric oxygen consumption rate must remain below the maximum usable oxygen transfer rate. Accordingly, the maximum allowable oxygen consumption rate, RO 2/3 max, is equal to the previously defined maximum oxygen transfer rate, JO 2/3 max. In the present bacteria fermentation example, assuming volumetric mass transfer coefficient KLA of 200 hour minus 1, a mean oxygen solubility of 12 milligrams per liter, and a minimal dissolved oxygen concentration of approximately 1 milligram per liter, the maximal oxygen transfer rate is estimated to be about 2.2 grams oxygen per liter hour. For feed sugar concentrations up to 20 grams per liter, the volumetric oxygen consumption rate remains lower than JO 2/3 max over the entire range of dilution rates considered. At higher feed sugar concentrations, however, the theoretical oxygen consumption rate exceeds the maximum oxygen transfer rate at intermediate and high dilution rates. Such operating conditions are therefore not feasible, as oxygen transfer becomes the limiting factor. The maximum oxygen transfer rate also sets the upper limit for the volumetric productivity attainable in continuous fermentation. Since at steady state, the volumetric oxygen consumption rate, RO 2/3, is equal to YO2 over X times the productivity prod X, the maximum attainable biomass productivity prod X max is given by prod X max equals JO 2/3 max divided by YO2 over X. In the present bacteria fermentation example, assuming a value YO2 over X of 0.7 gram oxygen per gram biomass, prod X max is estimated to be approximately 3.1 grams biomass per liter hour. As previously observed for the volumetric oxygen consumption rate, for feed sugar concentrations up to 20 grams per liter, the productivity prod X remains lower than prod X max over the entire range of dilution rates considered. At higher feed sugar concentrations, however, the productivity is limited by prod X max above a critical dilution rate. This critical dilution rate decreases as the feed substrate concentration increases, reflecting the growing oxygen demand associated with higher biomass production. The maximum attainable steady-state biomass concentration, X max, is determined by the ratio between the maximum allowable volumetric oxygen consumption rate and the specific oxygen consumption rate, QO2. Since the maximum oxygen consumption rate is equal to the maximum oxygen transfer rate, the maximal biomass concentration can be written as X max equals JO 2/3 max divided by QO2. The specific oxygen consumption rate is related to the specific growth rate through the stoichiometric coefficient YO2 over X. Under steady-state continuous operation, the specific growth rate is equal to the dilution rate, mu equals D. The maximum attainable biomass concentration therefore becomes X max equals JO 2/3 max divided by the product, D times YO2 over X. This expression shows that the maximum biomass concentration increases as the dilution rate decreases, since lower dilution rates correspond to lower specific growth rates and consequently lower specific oxygen consumption rates. Compared with batch fermentation, continuous cultures therefore offer the possibility of achieving higher biomass concentrations by operating at reduced specific growth rates. To conclude this section, based on the preceding analysis of oxygen transfer limitations, what constitutes the optimal steady-state operating conditions for continuous fermentation? When the oxygen transfer bottleneck is taken into account, the maximum achievable fermenter productivity prod X max is directly determined by the maximum volumetric oxygen transfer rate, JO 2/3 max. Under these conditions, the maximum productivity is independent of both the dilution rate D and the feed sugar concentration S feed. At this maximal productivity, it may be advantageous to increase the steady-state biomass concentration X max by reducing the dilution rate. This strategy requires increasing the sugar concentration in the feed in order to sustain the higher biomass level. For example, at D equals 0.35 hour minus 1, a biomass concentration of approximately 9 grams per liter can be achieved, with a feed sugar concentration of about 20 grams per liter. At D equals 0.10 hour minus 1, a much higher biomass concentrations close to 30 grams per liter can be reached, with a feed sugar concentration of around 60 grams per liter. It is important to note that the biomass concentration achieved during fermentation has a direct impact on the cost and performance of downstream processing operations. Consequently, if production cost is the ultimate optimization criterion, the optimal operating dilution rate and feed substrate concentration cannot be determined based on fermenter performance alone. Optimization of continuous fermentation therefore requires an integrated economic evaluation of the entire production process. In this tutorial, you explored the fundamental principles, kinetic characteristics, and optimization strategies of continuous fermentations. Continuous fermentations can be operated for extended periods under substrate-limited conditions, while maintaining stable steady-state concentrations, provided that the cells can stabilize at a specific growth rate equal to the dilution rate D, defined as the ratio of the medium flow rate Q to the reactor volume V. This condition requires the dilution rate to remain below the maximum specific growth rate, mu max of the cells. Two key operational variables govern steady-state continuous fermentations: the dilution rate in the feed sugar, carbon source concentration. The dilution rate alone determines the residual sugar concentration in the reactor, whereas the feed sugar concentration controls the steady-state biomass concentration. Under aerobic conditions, the attainable steady-state biomass concentration is ultimately limited by the maximum volumetric oxygen transfer rate. Once this oxygen transfer limit is reached, the maximum achievable fermenter productivity becomes independent of both the dilution rate and the feed sugar concentration. These two variables, however, continue to strongly influence the steady-state biomass concentration. A key feature of continuous fermentation is therefore the ability to increase biomass levels by reducing the dilution rate, or equivalently, by operating at lower specific growth rates. If interested, you can gain a deeper insight in the scale-up of microbial fermentations by enrolling in the online courses Digital Scale-Up and Optimization of Microbial Fermentations, or Simulation, Scale-Up and Optimization of Fermentation Processes. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.